Hello everyone, in this video we'll see about the characteristic table and excitation table of JK flip-flop. So when no clock pulse is applied at the input, then irrespective of the value of J and K, the output Qn plus 1 will be equal to Qn. Qn plus 1 is the next state and Qn is the present state. So when no clock pulse is applied, the next state will be equal to the present state, or it will act as a memory or hold. And when a clock pulse is applied, then we'll consider the four cases, that is 0, 0, 0, 1, 1, 0 and 1, 1. Here we are considering a positive edge triggered clock, as the clock applied is a positive edge triggered. So we have drawn like this. If it is a negative edge triggered clock, we can draw it like this. So corresponding to 0, 0, J is equal to 0 and K is equal to 0. The next state Qn plus 1 will be equal to the present state Qn. So it will again act as a memory or hold corresponding to 0, 0. And when the J input is 0 and K input is 1, then the output Qn plus 1 will be equal to 0. And if it is 1 and 0, then Qn plus 1 will be equal to 1. So these two conditions corresponds to the SR flip-flop. So in SR flip-flop, when S is equal to 0 and R is equal to 1, the output will be equal to 0. And when S is equal to 1 and R is equal to 0, the output will be 1. So here we can write J corresponds to S and K corresponds to R. So these two conditions are similar to, these three conditions are actually similar to SR flip-flop, and this fourth condition is different. And in this fourth condition is when J is equal to 1 and K is equal to 1, then the output will be equal to Qn bar. So if the previous output was 0, then the present output will be 1. Or if we say if the present output is 1, then the next output, that is the output after the clock pulse is given, that will be equal to, if it was 1 earlier, then after clock pulse is given it will become 0. So that is the truth table of a JK flip-flop. So now we'll write the characteristic table. So the characteristic table will represent Qn plus 1 in terms of Qn, J and K. So there are 8 possible combination of input. So 0, 0, 0, 0, 0, 1. So we can write the characteristic table from the truth table of JK flip-flop. So corresponding to 0, 0, in all these cases we are assuming that there is a clock input given. So corresponding to 0, 0, the output Qn plus 1 will be equal to Qn. So here Qn is equal to 0, so the output will be equal to 0 itself, corresponding to 0, 0 from this condition of truth table. And next is 0, 1. So corresponding to 0, 1, whatever be the value of Qn, Qn plus 1 will be equal to 0. And if it is 1, 0, Qn plus 1 will be equal to 1. So that is this condition. And when it is 1, 1, J is 1, K is 1, then Qn plus 1 will be equal to Qn bar. In this case Qn is 0, so Qn plus 1 bar will be, so Qn plus 1 will be 0 bar, so that will be equal to 1. Next case, J is 0 and K is 0. So here output Qn plus 1 will be equal to Qn. So here Qn is 1, so the output will be 1. Next case is 0, 1. So irrespective of the value of Qn, when J is 0 and K is 1, output will be equal to 0. And when J is 1, K is 0, output will be equal to 1. And when it is 1, 1, output will be equal to Qn bar. Here Qn is 1, so the output will be equal to 0. Qn bar is 0. So this is the characteristic table of a JK flip-flop. Now we can find the characteristic equation. So for that we can draw the K map. So this is Qn and this is JK. So we have drawn the K map for Qn plus 1. So this is 0, 0, 0, 1, 1, 1, 1, 0 and 0, 1. So corresponding to 0, 0, 0, output is 0, next is 0, 1, 1, 1, 0, 1, 0. So now we have to do the grouping. So we can do grouping like this. We can group these two ones together and we can do the grouping like this too. So all the ones have been mapped. So we can write the expression for this. The expression will be here 1 and 1 is common, that is j, and this is qn bar. So this expression is j qn bar, and here in the first and the last column 0 is common, so that is equal to k bar corresponding to this, and this is qn. So k bar qn. So we can write qn plus 1 is equal to j qn bar or k bar qn. So this is the characteristic equation. So that is qn plus 1 in terms of j, k and qn. J qn bar or k bar qn. Next we will see the excitation table of JK flip-flop. So excitation table is, will be writing qn and qn plus 1, and corresponding to each condition of qn and qn plus 1 will find j and k. So there will be 4 conditions 0 0, 0 1, 1 0 and 1 1. So corresponding to 0 0 we will be writing the excitation table from the characteristic table. So corresponding to 0 0 qn 0 and qn plus 1 0. And the second case is also qn 0, qn plus 1 is 0. So for these two cases, we can see that j is 0, but k is 0, 1. So we can write j as 0, but k is 0 for one case and 1 for the other case. So we can write k as don't care. It can be 0 or it can be 1. So next is 0, 1. So corresponding to qn 0, that is this case, and qn plus 1, 1, that is this case. We can see that here in this case, j is 1 and k is 0, 1 again. So we can write again k as don't care. Now we'll take the next case, that is 1 0. So this is 1 0, qn is 1 and qn plus 1 is 0. This is also 1 0. So for this case, if we check, we can see that j is 0 for one case and 1 for the other case, but k is 1 for both cases. So we can write k as 1, j is 0 for one case and 1 for the second case. So we can write j as don't care. Now the last condition is 1 1. So 1 1 is qn is 1 and qn plus 1 is 1. So these two are those cases. So correspondingly we can see that j is changing from 0 to 1, but k is same, k is 0. So we can write k as 0 and j as don't care. So this is the excitation table of JK flip-flop. So it is 0 don't care, 1 don't care 1 and don't care 0. So one way to remember this is, we can move from top to bottom. It will be 0 1 don't care for j, and if we move from bottom to top for k, then it would be again 0 1 don't care. So this is a easy way of remembering the excitation table, and we have to study this table. We'll be using this for the design of counters and conversion of flip-flops, and this excitation table is very, very important. So that's all for this video. Thank you.